Welcome to the lesson on automation challenges. Upon completion of this lesson, learners will be able to identify some factors that create automation challenges in manufacturing environments and describe solutions to overcoming some of the automation challenges. Learners will also be able to analyze case studies related to automation challenges. Automation in manufacturing presents both opportunities and obstacles that engineers must carefully navigate. Automation faces several challenges across the production spectrum. These range from foundational issues in basic part handling to the complexities of implementing advanced control systems. Each of these challenges requires specific technical solutions tailored to the particular application. For any successful automation implementation, a thorough understanding of these challenges and their potential solutions is essential, allowing manufacturers to develop effective strategies that optimize their automated processes. Here are some of the challenges that will be discussed in this lesson regarding automation in manufacturing. They include challenges in dealing with structured versus unstructured parts presentation, which impacts how robots interact with components, and handling widely divergent objects that require flexible automation solutions. This lesson will also look at challenges with conveyor belt systems, complex sensing requirements for automation, integration between different machines and systems, programming logic complexities, and the implementation of advanced force controls. Understanding the difference between structured and unstructured parts presentation is important for effective system design and automation. Structured parts are those presented in an organized, predictable manner, typically arranged in specific patterns within trays, pallets, or fixtures. Each component has a defined position and orientation, such as parts in molded trays or components in organized racks, making them easier for automated systems to handle. In contrast, unstructured parts are randomly positioned and oriented, often found loosely placed in bins or containers without any predetermined arrangement. These might include loose parts in boxes, mixed components in bins, or randomly piled items, which present a significant challenge for automation systems due to their unpredictable nature and the complexity of identifying and manipulating them. Let us look at some of the challenges posed by unstructured parts in automation. While humans can easily toss objects into a box and retrieve them later, robots struggle significantly with this task. When handling unstructured parts, robots must calculate new grip points and paths for each pick, which considerably slows down operation speed. The varying orientations of parts demand flexible gripping solutions, making end effector design particularly challenging. Moreover, success rates for unstructured picking are typically lower than with structured arrangements, which can result in significant production delays and reduced efficiency. Several technological solutions have been developed to address the challenges of handling unstructured parts in automated manufacturing environments. Implementing standardized trays and fixtures creates a more organized presentation system that allows robots to locate and manipulate parts with greater accuracy and efficiency. Advanced vision systems equipped with sophisticated cameras and sensors enable reliable part detection through complex algorithms, though this requires significant computational power and processing time. Machine learning algorithms have revolutionized object recognition by allowing systems to learn from experience and improve their ability to identify and handle various part configurations and orientations. Structured lighting systems illuminate work areas to minimize shadows and improve contrast, thereby improving the visibility of parts for both vision systems and machine learning algorithms to function effectively. Let us now look at the second challenge in automation, dealing with widely divergent objects versus uniform ones. Uniform objects present a limited number of known regular shapes that are easily handled by both humans and robots. In contrast, widely divergent objects consists of a broad range of irregular, deformable, and fragile parts. These, while manageable for humans, pose significant challenges for robotic systems. The key difficulty lies in programming robots to handle this variety, as they require high predictability and specific programming for each unique shape. Robots need extensive programming and adaptation for each new part variation, unlike humans who can naturally adjust their handling approach. Here are some examples of widely divergent objects found in EV manufacturing. These include large, rigid battery modules, delicate sensor wires and connectors, flexible cooling tubes, various sized fasteners and brackets, soft insulation materials, and fragile electronic control units. Let us examine the key challenges with handling widely divergent objects. Each component requires its own specific handling techniques. Materials vary greatly in their properties, from rigid metals to flexible cables and delicate electronics. Many parts can be easily damaged and need careful handling procedures. Robots require different end effectors or grippers for handling various component types. Complex programming is necessary to manage all these different handling requirements effectively. Several solutions exist to handle widely divergent objects in automation. Flexible gripper designs allow robots to manipulate multiple shapes with a single end effector. Quick change end effectors enable rapid switching between different handling tools. Vision-guided robotics provide adaptive control for varying part positions. Standardized packaging and presentation methods help create more predictable handling scenarios. The next challenge involves conveyor belts in factory automation. A conveyor belt is an automated material handling system that continuously moves parts, products, or materials between different points in a manufacturing process using a powered looping belt or roller structure. Conveyors are common in factory automation. While they are often assumed to be the best way to present objects to robots, they can present significant integration challenges. Handling moving items on the belt for picking, placing, or processing requires complex coordination. Some of the solutions to address conveyor system challenges include implementing synchronized motion control systems. Vision tracking enables reliable monitoring of moving objects. Smart sensors provide accurate part detection capabilities. Modular conveyor designs offer flexibility for different manufacturing needs. Guide rails and gates ensure proper positioning of parts during transport. The fourth challenge in automation systems involves complex sensing. Complex sensing functions similarly to the human eye. Human optic nerves require specific triggers to transmit information to the brain. Robots utilize fixed laser light camera systems for vision capabilities. Laser systems enable robots to detect and identify objects in their environment. Listed here are some of the challenges faced in complex sensing systems. Variable lighting conditions in manufacturing environments can impact sensor accuracy and reliability. Dust, smoke, and debris present in industrial settings interfere with optical sensing systems. Vibrations from heavy machinery can disrupt sensor calibration and alignment. Temperature variations affect sensor performance and measurement accuracy. Robotic vision systems have a limited field of view compared to human vision capabilities. Automated systems struggle to differentiate between objects with similar appearances or characteristics. Reflective or transparent materials create difficulties for vision systems to process accurately. Depth perception and 3D recognition remain significant technical hurdles for robotic sensing systems. Some of the solutions that can be implemented to tackle complex sensing challenges include multi-sensor fusion systems combining multiple sensing technologies for object detection. Advanced cameras equipped with 3D capabilities allow better depth perception and object recognition. Smart sensors with built-in processing capabilities enable faster and more efficient data analysis. Redundant sensing systems ensure reliability by providing backup measurements and cross-validation. Let's move on to the next challenge: systems integration in manufacturing automation. Systems integration involves combining different machines, robots, and systems to work together as one coordinated unit to achieve manufacturing goals. This process becomes challenging because different machines often use different communication protocols, control systems, and interfaces that must be synchronized. Here are a few challenges related to system integration. Starting with physical interface challenges, robots must precisely interact with human-designed interfaces like buttons, doors, and controls that weren't originally designed for robotic operation. The system requires accurate positioning and careful force control for these interactions. Improper calibration of these interactions risks costly equipment damage. Communication challenges in integration arise from several technical factors. Multiple communication protocols exist between machines, including digital I/O, field bus, and Ethernet systems. Legacy equipment often faces compatibility issues when integrating with newer systems. Precise timing synchronization between robots and machines is critical for coordinated operations. Signal reliability and effective error handling are essential for maintaining system stability. Safety considerations require implementing emergency stop functionality, fail-safe mechanisms, and human access control during automated operations. Several solutions address integration challenges in automated systems. Standardized communication protocols and universal robot interfaces help resolve compatibility issues. Modular system design and open architecture control systems enable flexible integration of different components. For safety, integrated emergency stop systems connect across all machines, while fail-safe mechanisms ensure equipment returns to safe states during failures. Access control systems with safety interlocks protect personnel during operation. Now, let us look at the next challenge: logic programming and automation. Logic in automation is a programming approach that defines how robots and automated systems process information, make decisions, and execute tasks according to predefined rules and conditions. Logic can be categorized into simple and complex types. Simple logic involves repetitive sequences, demonstrated in the left image showing a robot performing basic pick-and-place operations between fixed points. Complex logic, illustrated in the right image with a robot making A-B decisions, involves multiple conditional inputs and decision points that determine the robot's actions. Programming complexity poses several key challenges in automation logic. Systems must process multiple sensor inputs simultaneously while managing complex decision trees with numerous conditions. Robots need programming to handle every possible scenario they might encounter in operation. Real-world variations often present unexpected situations that must be addressed. Creating robust logic for actual operation requires extensive testing of all possible condition combinations. Some of the solutions that can be implemented to address logic challenges include simplified programming interfaces that make automation programming more accessible and user-friendly, ideal for operators with limited coding experience. Pre-built function libraries provide ready-made code blocks for common tasks, significantly reducing development time and potential errors. Visual programming tools offer intuitive drag-and-drop interfaces for creating logic flows, making program development and troubleshooting more efficient. Standardized programming templates ensure consistency and provide proven frameworks for common automation scenarios, reducing development cycles and improving reliability. The last challenge discussed in this lesson is advanced force control in robotics. Advanced force control refers to the precise management of robotic force during movements and tasks, which can be categorized into simple and complex operations. The left image shows simple movement without force application, where a robot performs basic pick-and-place operations along defined X, Y, Z coordinates. The right image illustrates complex force control, where F indicates force being applied during tasks like polishing, grinding, and precision assembly, requiring careful regulation of pressure during movement. While simple movements focus on positioning accuracy, complex tasks demand sophisticated force feedback and control mechanisms to maintain appropriate pressure throughout the operation. Here are some of the challenges related to advanced force control in automation. Maintaining precise force levels as the robot is in motion is important. Different tasks require unique pressure profiles for operations like polishing, grinding, and assembly. Too much force can damage parts, while too little force fails to complete the task. The automation system must be able to adapt to varying materials and surface conditions it encounters. For example, when polishing a metal part, the required force will need to change based on the hardness and texture of the material. The system has to continuously monitor and adjust the force to maintain the appropriate pressure profile. The system needs to provide consistent pressure throughout the entire operation from start to finish. Fluctuations in force could lead to inconsistent results or damage. This requires sophisticated sensors and control algorithms to precisely modulate the force in real time. Here are some of the solutions for the advanced force control challenges in automation. Force or torque sensors. These sensors can measure the forces and torques being applied by the robotic system during operation. By integrating these sensors, the automation can monitor the force levels in real time and make necessary adjustments. Advanced control algorithms can dynamically adapt the force profiles based on changing task requirements, material properties, and surface conditions. These algorithms use feedback from the force or torque sensors to continuously optimize the force application. Real-time feedback systems provide immediate information about the current force levels and allow the control system to make rapid corrections. This enables maintaining the target force profile throughout the entire operation. Another solution is to use end-of-arm tools and grippers that are designed with built-in compliance and force sensing capabilities. This allows the automation to apply the appropriate amount of force while also being able to detect and respond to changes in force requirements. Now that we have seen all the challenges faced by industrial automation, let's look at one of the case studies of a company, Walt Machine Inc., related to handling large orders with tight deadlines. The key issue that the company was facing was the need to rapidly fulfill sizable customer orders while also dealing with internal staffing and training challenges. The company was receiving large orders that required quick turnaround, but their employee training program was taking too long, causing staffing shortages that prevented them from keeping up with these tight deadlines. To address their operational challenges, Walt Machine Inc. implemented an innovative automation solution. They deployed a UR-10 robot equipped with a Robotic wrist camera and a 2-finger 140 gripper to completely automate what was previously a manual process. This robotic system transformed their manufacturing workflow by performing a series of complex tasks. First, it uses the camera to precisely locate parts on the table, then picks up these parts with its gripper, loads them into the CNC machine, initiates the machining process, and finally retrieves the finished parts. The most significant advantage of this solution is its ability to operate continuously, allowing Walt Machine to meet tight deadlines and handle large orders with unprecedented efficiency. By eliminating manual handling and introducing this advanced robotic system, the company overcame its previous staffing and productivity limitations, creating a more streamlined manufacturing process. In summary, automation in manufacturing faces significant challenges, including handling unstructured and divergent objects, managing complex sensing requirements, integrating sophisticated systems, developing advanced logic, and controlling force precisely in typical manufacturing environments. Despite these challenges, innovative technological solutions are emerging. Advanced sensors and simplified programming approaches are providing effective ways to overcome the traditional obstacles in industrial automation. The future of manufacturing automation lies in developing more adaptable, intelligent systems that can handle variability, complexity, and precision simultaneously. Successful automation requires a holistic approach that combines sophisticated hardware like advanced sensors and compliant end effectors, intelligent software, and a deep understanding of specific manufacturing processes. Continuous innovation and a willingness to rethink traditional manufacturing approaches will be critical in overcoming the current limitations of industrial automation. Thank you.